Hello everyone, and welcome to our Moxy Researchers webinar titled HIIT Protocol Pilot Data, presented by Dr. David Bellar. Dr. Bellar is the director of the School of Kinesiology at the University of Louisiana. He is also the Patrick Rutherford BORSF Endowed Professor in the School of Kinesiology there. Dr. Bellar recently presented at our Moxy Summit this past May, and that presentation has inspired some great discussions on the concept of non-involved muscles. So we're really looking forward to his follow-on presentation today. So our format for today is that Dr. Bellar is going to cover about half of his presentation, then we'll have a short break for a couple of questions in the middle. Then we'll finish up the presentation with a longer Q&A session at the end. And just a reminder that you can type in your questions on the right side of your screen. There's a questions panel where you can type those in, and you can type them in at any time, and we'll queue them up for the Q&A sessions. This webinar is being recorded, and we will post the recording on our website and on the Moxy Researchers Group forum. So with that, I will. One more thing. We will try to get this wrapped up by about 1:45, just so you have an idea of our time frame here. So with that, I will turn it over to Dr. Bellar.
Can you hear me?
Yep, your sound's coming through fine.
Okay.
And we just lost your screen though.
Oh, that's because PowerPoint crashed. Let's
try
that one again.
Small technical difficulty.
Can you see the presentation now?
Yep, we can see it now, but it's not in full screen mode.
I'll try full screen mode here one more time. Let me try one here real quick.
Looks like you're crashing again.
Yeah, I may have to just make that original view bigger.
Sure, that should work just fine.
If I can get my screen back. There we go. All right, let's just...
There you go. That's a good view.
Yeah, we can try that, and hopefully that sort of works. Okay, so this is actually the first webinar I've ever done, so the fact that it started off with my computer crashing, I think, is fairly appropriate. Normally, I'm a chalk on the chalkboard type lecturer, so the fact that I'm speaking to people from all over the country and who knows all over the world is kind of a novel thing and a neat thing for me. But what I'm going to talk about is some interesting pilot studies that we did after we left the Moxy Researchers Summit that we attended not too long ago. And it's really kind of a unique opportunity as a researcher to be able to basically talk to you all about how we went into the lab and basically played with the Moxy sensors and got some data around some unique questions that were generated. And Roger had mentioned that some of what we were playing with was non-involved muscles, but then also we were messing around with HIIT protocols as well with some of the some of our sensors in the lab. And so this is kind of an organic exploration and curiosity that we had when we got back, and so it's kind of neat to be able to talk to you about that. But first, I want to kind of go over what I'm going to talk about, which is to review Moxy's usage, how we've been using it, how a lot of other people are using it, what the value of using the device is. Then we'll go into our pilot studies. The first one being where we looked at involved versus non-involved muscles while using the devices. And then also to look at a unique study that we did, a case study we did with the device while monitoring HIIT training. And then, of course, we'll have conclusions, and there'll be plenty of time for questions and answers and all those types of things as well. And we're going to have some fun with the presentation, so it should be a nice kind of lighthearted affair. So to start off with, and I talk about this all the time, and I've been all around the world talking about this, but being frank and honest, most coaches or people who work with athletes who are training them are kind of stabbing in the dark. a lot of people think they know what they're doing, but when it comes down to it, if you keep questioning and peeling back the layers of the onion of, well, why are you doing this training? How do you know this training is working? Eventually you get to the point where they don't know anymore. They may be able to give you a couple answers to begin with, but after that, they're not really sure. Case in point, I just analyzed some data from an Olympic Federation where they really thought that their on-land testing was going to be associated with their on-water testing. So they had a group of water sports athletes, and they were testing them in the lab, and they were testing them on the water, and they thought, oh, this should work really well together, and we can just monitor them, you know, in the off-season. They don't have to be on the water. Well, it turned out that they've been doing that for 10 years, and the tests weren't related at all. And so they had a whole 10-year history of data that was essentially meaningless. They just assumed that it was going to work, but they had never actually bothered to take a look at the data and see whether it happened, and so see whether it actually was working. And so they were obviously not very happy when I told them that information, but you know, that's unfortunately the reality of where we're at. Most federations don't understand long-term athlete development, they don't understand athlete monitoring, and they don't understand the role of data and science in coaching. And I teach my classes here all the time that we really have to view the role of coaches and people who work with athletes as modifiers of human physiology, right? We know a lot of other professions that we you know, understand that that's true. Physicians, nurses, we completely understand these people go into a medical setting and their job is to modify the way your body is working, to heal it, to make it better, to alleviate an illness. Well, coaches are modifying physiology to make people perform better, right? Oftentimes in ways that the body was not really designed to perform to begin with. Right? So if we don't have a good, strong understanding of human physiology, it makes sense that we're not going to be very successful in that role. And it also makes sense as to why we have anecdote replacing data all the time when we're talking to coaches, right? It's really hard for a coach to understand data if they don't have a basis in human physiology. Right? There are some countries now that are doing a much better job of integrating from the ground floor up the acquisition of scientific data in coaching. Australia is a great example at the moment. They have poured money into the Australian Institute of Sport, hired researchers from all over the world, including harvesting many great sports scientists from the United States, and transplanting them over into Australia, and they've had a wealth of success as a result of that. And so in many cases, complacency is the enemy, and we see coaches attributing random success as part of a planned and repeatable scenario, which we know is just not the case. Now, where does Moxy fit in here? Right? A lot of times when sports scientists talk to coaches, they're talking about pieces of equipment that can't be taken out into the field, that you require a master's degree to really understand how they operate, that are incredibly expensive, and that are laborious to use. That's never going to work for the coach, so we can't really blame the coaches for not jumping on board and saying, well, I have to go out and buy a metabolic cart for my facility, or I have to have all these force plates, or I have to have a biomechanics video capture system. Like, okay, so taking that aside, if we have a very simple sensor that requires basically adhesive and isn't very expensive, but gives you the data of what's actually happening in the muscle that you're trying to train, that's something that I think everybody can get on board with. And so I think this is a good way to bridge the gap there and say, well, some tests are in the laboratory and that's fine, but there are ways the coaches can get real physiological data to back up the choices they're making with their athletes. And it's a good way to start making progress towards bringing more sports science in and replacing some of that anecdote with actual data-based decision-making. So that's why I really like the device, and that's kind of where our lab comes into the picture as well. All right, so the best coaches and trainers are curious and they question. Well, the best sports scientists, not that I'm saying I'm one of the best, but the best sports scientists are insatiably curious. And so, back a number of years ago at the NSDA conference, I ran into the little booth where they had the Moxy sensors, and I said, wow, that's really cool. That made me curious. And we came across a couple of research studies where, we thought we could incorporate that technology. And we bought some of the sensors, and lo and behold, we started playing around with them. We were just sitting there in the lab, me and Dr. Greg Davis, who I'll mention later in the presentation, a couple of other our researchers and graduate students. And we were just amazed at how easy they were to use and how much information we could get out of them. And so our next question was, as researchers, is can we take this data and use it in a research capacity? So when we talk about research grade instrumentation, the one thing that's always on the tip of the tongue is it reliable and is it repeatable? Right? And also, is it valid and accurate? And so as we started to play around with these things, right, we started to question that, and I'll talk about that on the next slide a little bit, the results of that. But what we also started to do was notice that we could really quickly pilot test things in the lab with these sensors and almost could take the place of using them in surface electromyography. Because we could put it on a muscle and see whether the muscle was active or not during the exercise by just looking at whether it was, the muscle oxygenation levels were going down. And so coaches, can use these in combination with other sensors, which is what we've been doing in the lab as an adjuvant to other research projects, to get a total picture of the stress during training. So what am I talking about there? Well, you can use these in combination with heart rate monitors. You can use these in combination with actually talking with your athletes about their perceptions of what's going on. You can use these in combination with temperature change, with, in our lab, hormone change, respiratory data change, physical performance, based on measurable outcomes like wattage on a cycle or power generated on a treadmill or isometric strength measurements on a force plate. So because they're so portable and they're small and they're non-invasive, you can use these in combination with a lot of other things. And it, as a coach, gets you a palette of information that you can build training around and also have a lot of data to look at. Another area that we thought about, particularly when we saw a couple presentations at the Researcher Summit, was HIIT training. So there was one presentation, I can't remember the gentleman's name who was giving it, but he was talking about using this during HIIT training. And it just immediately clicked to me that this was a great way to monitor quality of effort. One of the things that we always struggle with as coaches when we're talking about interval training is what's the rest of work ratio? How are we if we're trying to work on quality of effort, how do we know that we're maintaining that? How do we know that we're not letting fatigue set in and having the athletes change technique to try and produce the same output? And so, the one thing about these sensors is it tells you immediately at the muscle level, right, the oxygen response, the uptake of the muscle was the same from effort to effort to effort. So it's a natural thing to use for that type of training, and we're going to get into that later. We actually kind of did a deeper dive with a case study on HIIT training, and I think we had some pretty interesting results from that. So again, the sensors are great. I'm sure as they continue to kind of roll out there and more people use them, people think of other things to do with them. It's amazing if you look backwards at the history of EMG and exercise physiology and exercise science. People have come up with so many different ways to use that technology. We started off as kind of a very similar thing, which was a simple sensor that you could place on people while they were actually exercising and moving to get data. And they've been an incredibly important tool for the last 20 years in exercise physiology. And I think this is kind of a jumping off point for a Moxy sensor to have a similar role. All right, so on to some actual laboratory data. So this is a poster that was presented, and I have to acknowledge Dr. Gregory Davis, who was the lead investigator on this, and then Amber Sharp, who's one of our graduate students. This was presented at the National Strength and Conditioning Association conference this summer, and what it was a test to see whether we could basically take the sensors, put them on the biceps, perform a prescribed series of activities, which in this case it was an occlusion, a high-intensity exercise, and a low-intensity exercise. Now, the exercise is just a bicep curl where the cadence is being controlled by a metronome. So it's not exciting exercise, but it's an exercise type that we can really control tightly. And so because we can do that, we can say the sensor is giving us the same information every time, which as a researcher is really valuable. Because if I'm getting the same information every single time out of the sensor, then I know that I can draw conclusions based off that sensor. It's also really important for coaches to know you don't want to make a change in your training based upon data that's just kind of, that you can't count on to give you the same information every time. So even though this seems like kind of a boring study, and probably when it was in the lab it was a little bit boring, it was nonetheless an important step for us to take before we started doing other things with the sensor. And so I just want to draw your attention to the figure. It's figure 1. It's the kind of black and white figure that's on the right-hand side of the screen. And what you can see there is a low, a high, and an occlusion. And this is just from subject 4 out of 6. And you can see that very much the responses look the same between those conditions. And that's what we saw across the board, across all 6 people. All right, so they did a low intensity, a high intensity, and an occlusion event, and then they waited a certain period of time and repeated them. And our question was, would they change? And the answer was no. And so this was a really good and important step for us to be able to use these sensors in other research projects to say that yes, these are reliable. The validity part, it's hard to, typically when you look at validity, you would want to do it against a gold standard measure, which in this case we really don't have access to. So what we did was, sort of a positive control proof of concept, which was we know, without a shadow of a doubt, that if we include blood flow in the arm, SMO2 should drop. And it should drop, if the protocol's the same, it should drop the same way every time. So that's why the occlusion was included in there, was to say that, that was kind of the validity component. We know that that should show us a strong positive result, and, that's what we saw. And so from this point forward, we knew that we had a device that was robust, that we could trust graduate students to put on people, and now we've even shown that we can reliably give this to undergraduate students in the lab and let them, start up protocols with them, and they do just fine, which is a great thing, for the coaching community. They are sometimes a little sensitive when you put it on, and if you don't do it quite right, you get some data dropouts and different things that happen, but the nice thing about these sensors is you can basically at any point on your body take the sensor, turn it on, start up the computer program, just hold the sensor against your body, and you'll get a reading. All right? That's a good sign that even if you don't get it 100% perfect, you're going to get some data. And so that's why we've been having undergraduate students do it. I even have a freshman undergraduate student who was doing some stuff with it this morning and did perfectly fine. Fixed it to a person right where we wanted her to and started capturing data with absolutely no issues. So moving forward from there.
Dr. Beller, I'm going to jump in here with a question. One of our attendees has asked, how was the percent SMO2 quantified for the repeatability study? Was it the absolute values, the absolute deltas, or the percent deltas?
So we actually dumped the raw data into a program and then collapsed it based on a moving average, and then ran what's called a repeated measures ANOVA to test whether there was any differences by time. And so depending on how technical or whether the technicality of how we did it would benefit at all, we essentially smoothed the data slightly and then told the computer what times what events were happening at, including rest, exercise of the high and low type, and then the occlusion. And then told the computer which one was trial 1, which one was trial 2, and then let the computer statistically analyze whether there were differences between the trials.
Okay, great, thank you. Just a reminder to everybody that you can type questions into the panel on the right side and anytime. And with that, we'll let Dr. Beller continue.
Okay. So one of the things that came up at the Moxy Researcher Summit a lot was the use of monitoring muscles during exercise and monitoring both prime movers and non-involved muscles. And so in this regard, there were a lot of people who were getting information by monitoring non-involved muscles, and we should backtrack here. A lot of times these are deltoid muscles during cycling, or something that you don't see as a prime mover. And so that's why I've kind of put non-involved in quotes there, because during cycling, if you put, EMG sensors on the body, which detect electrical activity in the muscle, you're basically going to get readings from everything. You can put it on your jaw and get readings out of the muscles that articulate your jaw. So, at any point in time, the body, as it's moving from side to side, the muscles are somewhat active. And so, maybe a better way to say it would be minimally involved, but I'm just kind of sticking with what was used at the conference in describing what we did. So there were a couple of researchers who were sitting back there who had done some blood occlusion studies and different things. We're in the back corner, and what our take on this was is that people are seeing SMO2 drop in non-involved muscles during exercise. That being indicative not of blood being shunted away from those muscles, but more so of those muscles being starting to become more and more active as the athlete is shifting technique to maintain power output, particularly in cycling. And so, the first thing that we did was we came back to the lab immediately. I think it was actually the day after we had flown back in, and we had somebody cycling, and they were going to be, had some Moxy sensors on them anyway. And so we, on the anterior deltoid, we had a Moxy sensor, and right in line with it, we attached an EMG. And what we saw as we did that study, which I don't have on this presentation, but I'm just going to talk you through it. What we saw was that when the SMO2 and the anterior deltoid started to drop, the electrical activity in the muscle started to rise. And what that told us was that the person on the bike was bracing a little bit harder with the upper body to help generate more force with the feet during the pedaling stroke. And that's why the SMO2 was going down, is because the muscle was becoming engaged in the activity, and more so engaged as we rode for 10, 20, 30, 40, this was a 60-minute ride, so they rode all the way out to 60 minutes. As the SMO2 continued to drop, we got to a point where we had reached the MVIC peak signal in the anterior deltoid on the EMG. So the MVIC signal is just you contract the muscle as hard as you possibly can isometrically and take a reading of the electrical activity. During the end of the cycling protocol, we had achieved that same electrical activity in the anterior deltoid. So we kind of had a thought that we were thinking along the right lines, so Dr. Davis and I said, well, let's do a simple approach with the same thing we had done with the reliability, which was let's look at bicep curl and see what happens if we hold a muscle completely still on the opposite side of the body during exercise. And so we did that. We have one male subject, and I know this doesn't seem like a lot of weight, but you should try this sometime on your own. Stick a metronome at 40 beats per minute and take a 10-pound plate and just try and curl it up and down for a few minutes. You'll quickly figure out how hard this actually can be. So we have a controlled cadence bicep curl. We have the back against the wall, with the elbows fixed by the side. We have one arm serving as the control, so that arm does not have a weight in it. It's not moved during the exercise. It's just held still at the side. And then we have the other arm, which is doing the curling activity. We fixed the Moxy sensor to the midline of the bicep muscle on both the control arm and on the side that was exercising. And then what we really wanted to see here was that to test, if the muscle is completely isolated, so if the arm is being held by the side, there should be, almost no activity in that bicep muscle on the control arm. Are we going to see a change in SMO2 indicating blood being shunted out of that muscle? Right? And so this here is what we got. I'm going to kind of play with the screen there to get it all on there. So kind of talking from the left side of the screen to the right, we have SMO2. The blue line represents the arm that's exercising, and the red dots represent the control arm. So the very first thing that we do, typically when we put these sensors on, is do a maximum isometric contraction just to make sure that we're getting a good signal out of both sensors. So you can see the first drop there is labeled as MVIC, so that's isometric contraction. All right, so we see a drop, and we see that it mirrors on both sides of the body, which is great. We've got good symmetrical data there. And then we enter into a rest period where both arms recover back to about the exact same place. Right? So now we start the first set of curls. And this one was actually 5 minutes long. So if you can imagine doing 5 minutes of bicep curls at 40 beats a minute, this was quite a struggle for the person to actually finish. And so we see that in the exercising arm, the blue line drops off dramatically and hits a point at the bottom where we have, a couple of seconds of fairly, steady data, almost a plateau at the bottom. And then it starts to rise a little bit as fatigue starts to set in. Notice what happens in the control arm. Not a whole lot. All right, so we notice that it goes up. It seems to go up a little bit at the beginning and then down a little bit at the end. But if you just look at the pattern across the entire red line or red set of data, you can kind of see that there's some noise going on in there, but there's not a real big change in signal consistently across. And so we really don't see much of a change in the control arm at all. All right, so then as that exercise starts, we see the overshoot in the exercising arms. The blood comes back in, and we notice that the control arm is just kind of hanging out steady. We couldn't ask the person to do 5 more minutes of bicep curls because it just wasn't going to be physically possible to repeat that. So we increased the cadence to 60 and dropped the time down to 90 seconds. And again, you notice, SMO2 in the exercising arm drops off dramatically, and we actually seem to, to see the control arm going up. Right? And it kind of goes up and then comes back down again. But again, what we're probably seeing there is just kind of noise. All right, so that stops. Again, we see the overshoot in the exercising arm. And then just to make sure that this person's arm was completely finished for the next few days, we did 3 more minutes of curls, but this time at 20 beats a minute. And you can see, again, we have exactly the same thing, right, where the exercising arm drops off and we don't see much of a change in the control arm. All right, so we can look at that data. We can look at the SMO2. We can look at the THB, and we basically see the same thing. Other than a couple of data points here, we probably had some artifact of the person moving. We got some funky readings in there. It's very much the same thing. We see the changing THB and only the exercising arm, and we see basically a flat line reading for the non-exercising arm. And so what this tells us is that in a uniaxial joint, essentially, with a very controlled motion, we're not demonstrating blood being shunted from the non-active muscle. Right, so criticisms of this. Well, it's a small muscle, and maybe we need a larger muscle, more metabolic stimulus to get the body moving to see that shunting response. And so, granted, we knew that was going to be a criticism to begin with, so we designed a second pilot study to again assess this. Oh, and one last thing. Go ahead.
I was just going to jump in with one question here quick before we get away from the graph. It says, for the graph, can Dr. Bellar speculate why the active limb oxygenation blue rises as fatigue sets in the working arm? How would fatigue increase oxygenation after the initial precipitation?
Well, part of the explanation for that is probably, so at 40 beats a minute, the metronome's going click, 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 and all we're asking the person to do is complete the repetition within the click, but there's a varying rate there, and so as the person actually fatigues, the angular velocity around the elbow joint is probably actually being reduced, in which case the muscle would not be working as hard, and so it would require slightly less oxygen as the work sets in. There's only so much you can do to control how a weightlifting exercise is being performed, and a metronome is probably a good way to do it, but if we took it a step further, we could do it on an isokinetic dynamometer, which would actually control absolutely everything about the exercise. So I think what you're seeing there is that the person is, at the beginning of exercise, is feeling pretty good. they're maybe even a little ahead of the metronome, or they're getting to the top of the thing and waiting for the beep, whereas at the end, they're just barely completing the repetition by the time beep sets in. And so there's probably a little change in rate that we could attribute to that increase in SMO2.
Okay, great. Thank you. We've got about 10 minutes left, so we save a little bit of time for Q&A at the end. So I'll hand it back to you.
Okay, so I think that means I'm talking too much. So just last thing here on this exercise, just to show you that we did have an increase in lactate during this. So you can see the green arrows on the bottom. We started off with a baseline at 2, and by the end of the bouts of curls, we had increased it a little bit higher than where it had started at, up to about a 7 or an 8 there. So it was taxing enough, even in the one muscle, to shift lactate levels, which are not the greatest measure in the world, granted, but just to show you there was some stress, metabolic stress going on there. So again, limitations, the bicep's not a large muscle. We did increase lactate, but the blood volume in the bicep is relatively small compared to whole body blood volume, so we wanted to do something with larger muscle mass. So in this case, we decided let's do some kettlebell swings because they do involve quite a lot of muscle in the body, but if we do them with just one arm holding on to the kettlebell, we can really control the action of the other arm and make sure that it's not moving. So we fixed one Moxy sensor to the midline of the bicep muscle on the control arm, which was just held still by the side during the activity, and then we monitored the vastus medialis on the dominant leg. And I have to give a shout out to my graduate student Jason, because he was the subject for this, and doing kettlebell swings to failure is not a fun thing to do. And here's what we saw. So again, we have our NBIC at the beginning there to track to make sure that we're getting appropriate signal. We have a rest period before we start the exercise, and then I've highlighted in the red circle the exercise from the vastus medialis, and we can see that while that drops down, and we get a little bit more constant signal there, plateau at the bottom. What we see is, not very much going on with the arm held by the side. So it actually seems to increase a little bit at the beginning, and then it kind of comes back down to the baseline level at the end. So, considering the amount of musculature that's involved in a kettlebell swing, from the legs to the lower back to the abdominal muscles, if we were going to see blood shunting, we would probably see it here. And you can also notice that he starts the kettlebell swings in about 5 minutes and 30 seconds on the data, and then he continues on to almost 8 minutes and 30 seconds. So he did this for 3 minutes straight, swinging a 35-pound kettlebell against a metronome. So we would really expect that if we were going to see some shunting action, we would have seen it here, but again, we didn't see anything. So what do we take out of this? Well, our controlled pilot tests do not support the hypothesis that non-involved muscles have blood shunted from them during exercise. In fact, under the normal fluctuations, the joint is not mobile. The SMO2 is relatively constant. However, in the field, how this can be useful is that, as people are reporting reductions in non-involved muscles during exercise, what they're really seeing is that those muscles are becoming active and engaged. And so that may indicate ahead of perception or ahead of a coach's eye that the athlete is modifying technique. And for a lot of sports, that's really important because we want the athletes to maintain constant technique for efficiency standpoints. And so we may be able to use these to start to target the very early onset of changes in technique to continue exercising. All right. So take-home message, monitoring non-involved muscles, probably better to say minimally involved, is a way to determine if and when they become active. While we're not suggesting shunting of blood, it does signal changes possibly in mechanics, so this information is really valuable. As changes in technique are often not desired, and isometric contractions, particularly tensing in the shoulder girdle during cycling, sometimes are hard to catch for a coach's eye, particularly if it's not an experienced coach. And so this may be even more valuable to young coaches, learning coaches, to have this type of data to help them develop their coach's eye. So anyway, that was the last thing we did with the non-involved muscle. And so the last thing I want to talk about is our more recent little pilot project on HIIT training. So here we have one male volunteer again, And this was 4 sprints at 350 watts and an electrically brake cycle ergometer. Again, we're monitoring vastus medialis. Um, the reason that we picked 350 watts was the individual only had a VO2 max of about 40 on a bike, and so this was a pretty challenging effort for them. They hit VO2 max, I think, at about 290 or so watts, and so we're well above VO2 max on all of these efforts. So how did we do this? Well, we had them sprint at 350 watts until we noticed that their SMO2 had a kind of bottomed out and plateaued as they had engaged in the interval. And then we after it bottomed out, we started to notice that things were not going, particularly well with the interval. We stop them, and then we let the SMO2 recover all the way up to a plateau to target the start of the next interval. So we're really using 2 plateaus in SMO2 to guide how this HIIT training is going. One, seeing a bottoming out of SMO2 to show that we're achieving the same quality. We wanted to really see the same level of SMO2 depletion with all 4 sprints. And in this case, we got it on the first 3. I think if we had a better athlete on the bike, we probably would have got it with a lot more after that. But this individual wasn't, a super fit, high-end athlete, so he bottomed out at the same place on 3 of the 4, and the 4th one, I think he was, about 10% higher or so when he bottomed out. And then we let him recover up until the oxygen, the SMO2 had reached a plateau during recovery on the high end. And then we took measurements kind of continually during this. So after every interval, we would do a finger stick, and we would look at the pH change in the blood and also the lactate change. And then during recovery, so after the 4 intervals were completely over, every 5 minutes for 15 minutes, we did repeated measures after that. All right, so our lactate concentrations and pH were taken from a capillary sample of the finger. Just to kind of reiterate the importance of doing these things right, and we cleanse the area first. We always discard the first drop of blood when we're doing any of these measures because it's not really, the first drop is never really representative of venous blood. So we always want to take the second one. We use the ANOVA Biomedical Lactate Plus after high and low control check to do the lactate. And then we have a neat system in our lab. We have a Ross glass microprobe electrode, which is something you can use for highly proteinated or protein-rich solutions to measure pH. We did a 2-point calibration on that, and that's nice because we can actually take 1 drop of blood and stick this little glass electrode in there, and it gives us the pH almost immediately. So, why were we looking at that? Because we wanted to see this. The blue line is lactate, the red line is pH. Lactate is really indicative of carbohydrate breakdown, or particularly glucose breakdown within the muscle. It gets a bad rap, but really it's just a 3-carbon molecule that carries energy. So high lactate levels really aren't that bad in and of themselves. When you're exercising really hard, your cardiovascular muscle loves to metabolize lactate. And your muscle itself actually has a shunting system where it can move lactate from a fast twitch fiber to a slow twitch fiber through a series of monocarboxylate transporters and use it for energy. And so it's really just a molecule that's carrying some of the energy from glucose. But what we wanted to see was, we know with sprints that lactate is going to change, but would we see a shift in pH if we did this? And so if you look here, we have baseline, exercise 1, 2, exercise 3, and then we have our recovery measures thereafter. And we noticed that the pH line really isn't changing that much. We have a massive change in lactate. And if we look at our pH on a different type of scale, what we kind of notice here is that there is a little bit of a drop from 7.75 to 7.4 during the exercise. But then if you were looking at this and seeing whether the athletes were kind of reliably duplicating the effort every time and being overwhelmed by the protocol, you would kind of see that every time you did an interval, the pH would continue to drop. But by using the Moxy sensor and using the guidance from the SMO2 data, what we really see is that we got the same quality of effort in terms of muscle oxygenation reduction, but we kind of didn't see that every single interval caused a serial decrease in the pH in the bloodstream. And so what that's telling us is that using the Moxy sensor is helping us maintain the quality while also helping us make sure that the athlete is not overdoing it during the protocol and essentially letting the pH change run away from them. And so we were kind of excited to see that, because a lot of times coaches really don't understand how to make sure that they're getting the same reliable, repeatable type effort out of interval training. And here what we're seeing is that using SMO2 is helping us kind of control the physiological responses to every interval and keep it a little bit more constant. All right, so the lactate response again was predictable. The pH initially declined, but then was fairly constant from interval to interval. And from this, we can really look at lactate to proton ratio, which is this guy right here. And so what we notice is that if we divide the lactate measurements by the pH, we get the same type of shape that we get when we look at just the lactate change on its own, which is the blue on the top line there. And so what that's really telling us is that the body is putting more lactate into the bloodstream as a byproduct of glucose breakdown. But because the shapes are so similar, what we're again seeing is that the body, the pH of the body, that product of the physiological response to the metabolic stress of the exercise really isn't changing very much. And so that was definitely something that we thought was very positive. So the take-home result of that, it appears that using SMO2 to guide the interval length and recovery period was beneficial. The subject was able to work at a high intensity well beyond the lactate threshold without overwhelming the buffering systems in the body, and this suggests a real value to using SMO2 to guide interval training to maintain quality of effort. So based upon our pilot studies so far, we can suggest monitoring non-primary muscles during exercise may be useful in determining changes in the mechanics, and using Moxy during HIIT training may be a way to gauge recovery and also to help maintain quality of effort. So with that, I'd like to thank people in our lab that helped. Dr. Gregory Davis is an assistant professor in our School of Kinesiology, Jason, who's my graduate assistant, and Alyssa, who's a young, promising undergraduate student in our lab, and be happy to answer any questions you may have.
All right, Dr. Beller, thank you very much for that presentation. I very much look forward to the continued discussion on these ideas. We've got a question here with respect to the HIIT training. Is pH change just due to a temporary increase in CO2 secondary? Oh, I lost it here. One second. So is pH change just due to temporary increase in CO2 secondary to the effort?
Okay. Not quite sure I follow that, but so pH change is a complicated thing. It starts with ATP breakdown causes increased protons to be built up in the muscle, and then some of those end up leaking into the bloodstream. Additionally, carbon dioxide, as it's produced as a byproduct of metabolism, is buffered in the bloodstream, which is what our bicarbonate does. So it's a complicated thing what causes changes in pH. There's multiple sources, and there's a very complicated buffering system that starts intracellular and works its way into the bloodstream. And so you can't really measure pH in the blood and say that one particular source of the protons was modified. But what rather we're saying there is that we didn't see any change in that system at all. And so what it's suggesting to us is that the buffering systems in the blood are not being overwhelmed by that exercise. And what you see a lot of times in very poorly designed HIIT training protocols, particularly if you look at track and field athletes, is that the stress after every interval compounds. And so the athlete is continually engaged in more stress, even though the goal of the interval training session was to maintain quality of effort. And so this may be one way to counteract that by saying that, look, when we did it this way and we used SMO2, there wasn't evidence of a compounding physiological stress, right? Taking lactate aside, which we know was going to build irregardless, looking at pH in the blood and seeing whether our buffering capacities in the blood are being overwhelmed, we didn't see any evidence of that. And so there needs to be a lot more investigation of this. Obviously, a pilot study of one is an interest point, But it does suggest this might be a way to help people avoid that scenario where their interval protocol starts off looking like one thing and they end up with something completely different after the 5th or 6th repetition.
Okay, we got a couple more questions here. In the upper body studies, you completely occluded the arm to look at the bottom out of SMO2. Is this possible for the lower body to see if it differs from exercise-induced bottoming out? Is there a methodological reason why you would do this?
Yeah, you can occlude blood flow on the. I mean, there are occluding cuffs that will fit on the upper thigh and can include blood flow there. And to be honest with you, you probably just find exactly the same thing. I mean, when blood flow stops, oxygen is going to decline. Your mitochondria never turn off. And so whether there's blood flow or not, they're going to continue to use oxygen until they reach equilibrium with the surrounding tissues. I guess we could, I don't think we would be interested in doing that. The reason we picked the upper body is because occluding cuffs, it's a lot more comfortable for the subjects to have the occluding cuff on the arm than up by their groin. And so from that point, it was just more, something we, thought would be more comfortable for people. But I don't think we would do that because I don't think we would find any more or any different data out of it. But it is possible.
Okay. Here's another one. Is the timing of the independent SMO2 and the lactate reading as it relates to the working muscle accurate to the timing of the working muscle so that they can be compared?
Well, so with the lactate, we took immediately at the cessation of the exercise. The SMO2, we obviously collected, the entire time during the exercise itself. To be honest with you, I try and get people to not look at lactate too much. Lactate's kind of overplayed. It's a point of interest. And from a researcher standpoint, lactate's nice because if you need to document that the exercise was in some way, shape, or form rigorous, you can just kind of prick somebody's finger, and if you get a lactate reading, they were actually, at least working decently hard. But from a training guidance standpoint, it's difficult to figure out. People with the most pronounced lactate responses actually tend to be the better athletes, and so a lot of times people are looking for lactate to be lower, and that's not necessarily what they ought to be looking at. There was a famous study, not that long, I guess it may be long ago now, but they looked at the World Championship 400-meter race, and they took blood lactate readings pre and post on them and found that all the guys that finished in the top had higher lactate readings than the guys who finished towards the bottom. And it's just because those people were more effective at turning over glucose during the race, and so they had more energy available in order to run faster. Another disadvantage to lactate is it has I think which may be what you're kind of alluding to, it has a limited sampling rate. I mean, you can only prick a person's finger so often and so many times, whereas with monitoring SMO2, you get readings constantly the entire time during the exercise, so you get a lot more feedback doing it that way. When we looked at it, lactate was at the end of the effort and SMO2 was continuous during.
All right, well that wraps up our time for today. Like I mentioned earlier, the recording of this will get posted online and it'll be on the forum as well. So if there's any follow-on questions, we can take that up from there. So thank you again, Dr. Bellar. This was a wonderful presentation, and we look forward to continuing to expand our knowledge base out of your labs.
Thank you very much.
All right, take care, everybody, and thank you to all of our attendees.